Welcome back to our series of physics tutorials. This video is a continuation of our previous one on displacement, velocity, and acceleration. A general rule is that the shape of every line segment from each of the displacement, velocity, and acceleration versus time graphs can be matched respectively up from left to right on the following relationship spectrum. From a curve to a straight slope line, then to a flat line, and then 0, 0, and 0. This means that if a displacement time graph was a curved line, the velocity time graph of the same time interval of the same object would have a straight slope line. An acceleration graph would show a flat non-zero line. Likewise, a flat non-zero line on a velocity time graph will represent a straight line on a displacement time graph, and a flat line at 0 on an acceleration time graph. Note that we assume displacement always starts at 0, and all movement demonstrated in the graph is relative to the object's initial position, regardless of what velocity or acceleration starts at. Don't worry if this doesn't make sense entirely yet. We'll go over an example in the next slide that will hopefully clear things up a bit. Here's another important tip to drawing the relationships of these graphs. The slope of a displacement time graph is the velocity at that point. The slope of a velocity time graph is the acceleration at that point. The area between the curve and the x-axis, which in this case is time, of a velocity time graph is the total displacement. Thus, the height or y value of a point on a velocity time graph is the change of displacement, or the increase or decrease relative to the previous displacement. The area between the curve and the x-axis of an acceleration time graph is the total velocity, and the y value of a point on the curve is the change in velocity relative to the previous velocity. Note that unless the acceleration or velocity time graph has a negative value, or when the curve goes below the x-axis, the slope of a velocity or displacement time graph respectively will not have any negative slope in the graph. In other words, the graph will never slope downwards and vice versa. Again, don't worry if this doesn't fully make sense to you. We'll go over it a lot more in the next few slides. As shown in the displacement time graph on the top right, the slope, drawn with the blue lines, on the left is positive, and thus the velocity on the left side of a velocity time graph is also positive, and has positive y values. Similarly, the negative slope on the right of the displacement time graph corresponds with the negative velocity values on the right. The total area under the velocity time graph curve, shaded in red, is equal to the total displacement. On the left side of the velocity time graph, the shaded area is positive because positive velocity multiplied by positive time gives a positive number. So the change in displacement, not to be confused with displacement, on the left side of the graph is also positive, meaning the object is moving forwards. On the right side of the graph, the area is negative because negative velocity multiplied by positive time results in a negative value. So the change in displacement is negative, and the object is therefore moving backwards. The slope of the velocity time graph is negative, sloping downwards. Thus, the acceleration value on the y-axis of the acceleration time graph is negative. The area under the acceleration time graph is equal to the total change in velocity, and so both are negative. The slope of the acceleration time graph is the jerk of an object. For example, if we were standing up in a bus that had just started moving, we would naturally lean forward, moving our center of gravity forward to counteract the backwards lurching effect or the slight jerk we would experience when the vehicle starts moving. However, I will not be explaining this topic in depth as it is beyond the scope of this video. Recall the relationship in the last slide between the slopes and areas of displacement, velocity, and acceleration versus time graphs. Knowing this, consider the following velocity time graph. If the slope of a velocity time graph is negative, the object is slowing down until it reaches a velocity of 0 meters per second. Also recall the relationship of a curve to a slope line to a flat line to 0, 0, and 0. Since velocity is a slope line, we know that displacement must be a curved line, and that it must eventually flatten out into a flat line when velocity is 0 meters per second. When velocity is 0, the object is not moving, thus displacement does not change. Now, we must determine whether the displacement graph slopes up and over at the beginning of the line, or if it slopes over and then up. In other words, we are trying to answer the question, does the displacement time graph have a large or small slope at the beginning? To determine this, we must analyze the slope of the velocity time graph. Since the slope of a displacement time graph is equal to its velocity at a given point, the slope of the displacement graph must be large at the beginning, then eventually decrease to 0, just like how the velocity is large at the beginning and decreases uniformly to 0. This means that the curve on the displacement time graph must be up and over and eventually flattening out. Oppositely, on the right side, the velocity time graph is slanting upwards in a straight line, meaning that the slope of the displacement time graph must start from 0 and increase to a larger slope. This can be seen on the top right, where the curve goes up and over, flattens out, then goes over and up. Acceleration is a lot easier than judging the displacement from a velocity time graph because since velocity is a sloped straight line, we know that acceleration must be flat lines. Flat, but not at 0. Since acceleration is the slope of a velocity graph, it starts off negative and then turns positive after the midpoint. Then we use a vertical line to connect the two horizontal lines like so. However, it is important to note that the velocity time graph is realistically impossible to replicate. The slope of a vertical line is infinite or undefined, demonstrating that there was an instantaneous change in acceleration. Since acceleration is the rate of change of a velocity of an object, it cannot be instantaneous. Imagine an object moving forward, but slowing down until it reaches a velocity of 0 meters per second. Immediately after it reaches that velocity, its velocity begins increasing again. In the real world, there is nothing such as instantaneous or immediate, besides our current understanding on quantum mechanics. Therefore, realistically, the velocity time graph would more likely have a downward slope at the beginning that shapes into a curve and flattens out to 0 meters per second. Then, after a small amount of time, the graph would curve and slope back up. If we translate the velocity time graph that I described above to an acceleration time graph, the corners of the right angles would smooth out to become curves, and the vertical line would be stretched to the right when a is positive and stretched to the left when a is negative, all while maintaining the same x-intercept, seeming to form a horizontal asymptote at a equals 0 or y equals 0, crossing the x-axis at the midpoint of the graph. Determine the displacement time graphs and velocity time graphs that correlate to the following acceleration time graphs. I suggest you pause the video and try these two for yourself. I'll reveal the answers in a few seconds. There are 4 main formulas that you can use to solve kinematic problems. However, utilizing the formulas is oftentimes not as simple as just plugging in values. You will need to be able to manipulate these formulas, and to do so, you must be familiar with the variables and how you can rearrange some of these equations to solve certain problems. Firstly, there is v equals u plus a times t. Then we can rearrange that to s equals u times t plus 1 over 2 a times t squared. Then we can also rearrange it into v squared equals u squared plus 2a times s. And lastly, the last variation would be s equals v plus u all divided by 2t. Though your teacher may allow the use of a formula booklet during an exam, it is still strongly encouraged to do practice problems to build your confidence with these types of questions, as 1D and 2D kinematics, work, energy, power, forces, and impulse are all very closely tied together, where each can be used in combination with another to solve more complex problems. We will be covering all these topics in future videos, so stay tuned. A late passenger, sprinting at 8 meters per second, is 30 meters away from the rear end of a train when it starts to pull out of the station with uniform acceleration of 1 meters per second squared from 0 meters per second. Can the passenger catch the train if the platform is long enough? And if so, between which time intervals are they able to get on the train? A hint is that you need to solve this using a quadratic. Firstly, we realize that we must have an equation where we can calculate the time intervals of which the passenger reaches the train. Next, we determine which variables we have and simultaneously decide which of the 4 formulas listed in the previous slide we should use. Let's start with v equals s divided by t and rearrange that to form t equals s divided by v. The s in this formula represents the entire displacement of which the passenger needs to travel to reach the same displacement that the train has. With this, we assume that the displacement of where the train had started when the passenger was 30 meters away is 0 meters. This means that at the very beginning, the position of the train was 0 meters, and the position of the passenger relative to the 0 is negative 30 meters, or 30 meters backwards. The point that these two objects meet is 30 meters more than the displacement of the train because the passenger starts 30 meters behind it, so the point is 30 meters further. Thus, we obtain the equation s equals ut plus 1 over 2 at squared plus 30 meters. Next, we plug into the formula v equals 8 meters per second, which is the passenger's velocity, not the train's, to obtain t equals ut plus 1 over 2 at squared plus 30 all divided by 8. This can be simplified by plugging in u and a, giving us t equals 0 times t plus 1 over 2 1t squared plus 30 all divided by 8. This equation can be further simplified and expanded to 8t equals 1 over 2t squared plus 30, and finally 1 over 2t squared minus 8t plus 30 equals 0, where we can use the quadratic formula to solve for the two values of t, which turns out to be t equals 6 and t equals 10. Thus, our final answer would be yes, the passenger can get on the train between 6 and 10 seconds after the train has started. Kinematics exists everywhere around us, and though we may not realize it, there is no instance where a physical object can be explicitly defined only within the scope of kinematics. If kinematics is defined as the study of the motion of objects without reference to the causal forces involved, the assumption that causal forces are not involved simply cannot be applied to the real world, as there is an unimaginably vast number of different forces acting on any object. For example, we not only experience the gravitational pull of Earth, but also the gravity of a book on our table, the gravity of our neighbor next door, the gravity of a wild raccoon on the other side of the world. Although the three latter examples have a significantly weaker gravitational pull than the Earth, a force of attraction between each and every one of these objects does exist. Therefore, kinematics cannot be used to explain something in the world without the inclusion of other relevant subject matters. We must accept that no single topic or theory in physics can stand independently. Everything encompassed within the scope of physics is interconnected. In fact, the word scope is used quite loosely, as there is really no fine line that divides physics and chemistry, physics and math, or even physics and geography. Kinematics is inherently tied to so many things we do in physics. From dynamics to mechanics and impulse to particle physics, the concept of kinematics is used in nearly everything pertaining to this field of science, as it provides a concrete basis for measuring physical movement. However, it almost always stands alone, and that is where the difficulty comes from explaining or analyzing any real-world example with only kinematics. That's all for the video today. Thank you for watching. See you in the next video.